Today we're going to be graphing rational functions, and I want you to recall the parent rational function. The parent rational function is y equals 1 over x. It's an odd function, so it's symmetrical about the origin. It's got a vertical and a horizontal asymptote, and that vertical asymptote is x equals 0, and that horizontal asymptote is y equals 0. So we're going to use this helpful acronym, AIM, to graph rational functions today. So what does each letter stand for? A stands for asymptotes, I stands for intercepts, and M stands for multiplicity. So I'm going to briefly go over what each of these, or what we need to do for each of these. So A stands for asymptotes. Remember that an asymptote is a line that the function will approach but never cross. So it'll just continuously approach it and get closer and closer and closer to infinity. It'll never cross it. Rational functions have a vertical and a horizontal asymptote, and here's what you need to do to find each of those. So the vertical asymptote is the solution to the bottom. So what you're going to do is set the denominator equal to 0 and solve for x, and you're going to write your vertical asymptote as x equals that number, because any vertical line is x equals the x value for every single point on that line. And this will affect your domain. So why do we do this? We do this because that x value that you would plug into the denominator is the x value that would create a 0 in the denominator. And remember, we cannot divide by 0. It is undefined. So that's your vertical asymptote. Your horizontal asymptote is when the degree in the denominator is higher than in the numerator, your asymptote is y equals 0. So some examples that I have right here, f of x equals 5 over x. I have a variable on the bottom, or in the denominator, and I don't on top. Or we have an x, and remember, if it's just x, that's x to the power of 1. And then the highest exponent for x on the bottom is a 2. So there's more on the bottom. That's what I like to say. When there's more on the bottom, your horizontal asymptote is just y equals 0. Now let's say there's the same. Your horizontal asymptote is going to be the ratio of the first terms. So some examples of this would be you have f of x equals x plus 4 in the numerator and x minus 2 in the denominator. So my exponent is 1. That's the highest exponent. So they're the same. Okay, so when they are the same, your horizontal asymptote is just the ratio of the first terms. So right here, the leading coefficient is 1. Leading coefficient is 1 in my denominator, and I would write that as y equals 1 over 1, which just simplifies to y equals 1. In the next example, we have the same type of situation, and so your horizontal asymptote would be, again, the ratio of the first terms, which would be y equals 3 over 4. So let's say this exponent right here was like a 2, and that was a 2. It'd still be the same thing, okay? It'd be the ratio of the first terms, or the leading coefficients. So one of the things that always confuses my students is that horizontal asymptotes apply to the ends of the graph. This means you could have a horizontal asymptote at y equals 0, for example, but you still might have an x-intercept. And we'll see some examples of those. But on the ends of the graph, on the left and the right, you won't have anything cross those asymptotes. So the next letter is I. What does I stand for? It stands for intercepts. So we're going to look for x and y intercepts. Remember, this is just where your function crosses each of those axes. So the x-intercept is going to be the solution to the top. Remember, the x-intercept is when y is 0. So if I were to plug in, let's say I have y equals numerator over denominator. If I were to plug in 0 for y, that would look like this. How do I solve for x if my x is in my numerator? If I get rid of this, I'm left with 0 equals my numerator. So I'm just going to solve for x in my numerator. So we're going to find the solution to the top, the solution to the numerator. So we'll set our numerator equal to 0, and we'll solve for x. Whatever we get, we'll write it as an ordered pair just like that, and we'll graph it on the x-axis. So your y-intercept is when x is 0. So we're just going to plug in 0 for x, we're going to solve for y, and we're going to write it as an ordered pair. And the very last letter stands for multiplicity. So multiplicity is just how many times something repeats. And what we're going to be looking for are factors with an even exponent, so a multiple of 2. So the entire factor needs to be squared or to the 4th power or to the 6th power. So we're going to circle some examples of factors with multiplicity. Remember, the entire factor needs to contain multiplicity. So here's an example right here. X plus 3 squared is an example. This always throws students off. Hey, but there's a 2 as an exponent. Is the entire factor squared? It's not. So that is a non-example. Same thing right here. That's a non-example. X squared, that contains multiplicity. X plus 4 to the 4th, absolutely. That's a multiple of 2. X plus 1 squared, sure. And x squared minus 9, that is not an example of a factor with multiplicity. The entire factor is not squared. So when we're looking at multiplicity, we're looking for these types of factors, the ones that are circled. So what if you have multiplicity in the numerator, which you're not going to see in Algebra 2, or not today, I'm sorry. So when factors have multiplicity in the numerator, the function will have a double root bounce at that root. So here, as you can see, there's multiplicity in the numerator, x plus 2 squared. And here's what my function will look like. You've still got a vertical and a horizontal asymptote, and you've got an x-intercept at -2. And what that function will do is it'll just kind of bounce off that root, come back, and then it'll slowly, forever and ever and ever and ever and ever, approach that asymptote, going to the left. When you have multiplicity, which let me make this a little smaller. When you have multiplicity in the denominator, for example, right here, x plus 2 squared, what happens is the function will meet or come together at that asymptote. So what you have here is an asymptote at x equals -2. That's the asymptote. And this function, as you can see, is on the same side of the horizontal asymptote. So that's what's different. Think about that parent rational function, remember, and you've got your 2, which I probably shouldn't draw it like that. I should probably draw it like, let's see, whoops. I should probably draw it like this. I've got my asymptotes here, and you've got that in that first like quadrant, if you will, and then you've got the other part of your function in that third quadrant, if you will. So when you have multiplicity in the denominator, what's going to happen is your function will meet at this asymptote. Let's say it'll meet there, and I like to say it's the same side of the horizontal asymptote. So let's write that down. The same side of the horizontal asymptote. So let's look at some examples. Let's graph some examples. Let's go to number 1. So these are just some basic examples. This first one is f of x equals 4 over x plus 2. So the first thing we're going to do is we're going to find our asymptotes, the vertical and the horizontal asymptotes. So the vertical and the horizontal asymptote. So what do we do to find the vertical asymptote? So if you refer to your notes, the vertical asymptote is going to be the solution to the bottom. So I'm going to set my denominator equal to 0, and I'm going to solve. Remember, this is the x value that would create a 0 in your denominator. So x plus 2 equals 0. When I subtract 2 from both sides, I get x equals -2. And let's go ahead and graph x equals -2. That is the vertical asymptote. Your horizontal asymptote is you're looking at the exponents basically in your variables, okay? So we don't even have a variable in our numerator, and we do in our denominator. So we know that there's more on the bottom, which means my asymptote is y equals 0. When there's more on the bottom, it's y equals 0. So the asymptote here is y equals 0. And now let's get into our intercepts. So the intercepts, we're going to have an x-intercept, and we're going to have a y-intercept. So the x-intercept is when y is 0. Remember, if I plugged in 0 for y, I would end up just finding the solution to the top. So we set our numerator equal to 0, and 4 does not equal 0. So actually, we do not have a an x-intercept in this particular example. It's not applicable. So let's look for our y-intercept. The y-intercept is when x is 0. So what I'm going to do is I'm going to plug in 0 for x. So 4 over 0 plus 2 is just 4 over 2, which is 2. So if I write that as an ordered pair, it's 0, 2. And let's graph that. And now let's look for any multiplicity. Do we have any factors that are either squared or raised to the fourth power? Do we have any of these special squared terms? We do not, so it is not applicable in this case. So now I'm just going to sketch this graph. I know that if I have a point, and this, let's call it this upper right quadrant, if you will, I know that it's going to pass through that point, and it, whoa, let's try that again. And it's going to slowly approach this asymptote and forever and ever approach this asymptote. I also know that since there's no multiplicity, that the other part of my function is going to be down here in the lower left. It's going to look something like that. You can always check by graphing it on your calculator and looking at your table of values, or just looking at your graph on your calculator. So, but that's what it'll look like. So let's move on to the next basic example. Number 2 is f of x equals x minus 3. So the first thing we're going to do is find our vertical and our horizontal asymptotes. So what do we do for that vertical asymptote? We're going to set our denominator equal to 0 and solve. X minus 3 equals 0, so the vertical asymptote is at x equals 3. Let's go ahead and graph that. X equals 3. And the horizontal asymptote, I can see that I actually have the same degree in our numerator and the denominator. For example, x to the power of 1, x to the power of 1, which means I've got the same. Let's go ahead and write that down so we can reference this whenever we're doing our homework. It's the same on top as it is on bottom. So the horizontal asymptote is going to be the ratio of the first terms. Remember, if nothing is in front of that variable, it's 1. So it's going to be y equals 1 over 1, which is just y equals 1. So my horizontal asymptote in this case, because it's the same, it's going to be, I'm going to go up 1, and then the horizontal asymptote is just a horizontal line that goes through that point, because every single point on that line is y equals 1. So now let's look for our intercepts. We're looking for an x-intercept and a y-intercept. So what do we do to find the x-intercept? The x-intercept is the solution to the top. So I'm going to set my numerator equal to 0, and that's easy enough. My point is just 0, 0. So my x-intercept is at 0, 0. The y-intercept is when x is 0, so I'm going to plug in 0 for x. And when I do that, I get 0 divided by -3, which is just 0. So my x-intercept and my y-intercept are the same. And now let's look for those special squared terms where the entire factor contains multiplicity. Do I have any of that? I do not. So the m in this particular problem is not applicable. So when I sketch the rest of this function, I know that I've got the two asymptotes here, the vertical and the horizontal, and I've got a point in this lower left quadrant, if you will. So I know it's going to pass through that point and approach this asymptote, and pass through that point and also approach that asymptote. And because there's no multiplicity, I know the function is not going to meet at this asymptote. I know it's going to be in this upper right quadrant. Okay, so it's going to look like that. Let's move on to example number 3. So example number 3 is another basic example, and we're adding a little bit each time. And let's look for our vertical and our horizontal asymptotes. So the vertical asymptote is the solution to the bottom. So I'm going to set x minus 4 equal to 0, and I'm going to solve for x, and I get x equals 4. So that's my vertical asymptote. Did I say that? That is the vertical asymptote. X equals 4. Now let's look for a horizontal asymptote. So would you say this is the same, or is there more on bottom when we talk about that highest exponent? It's the same, right? X to the power of 1, x to the power of 1. And because it's the same, this horizontal asymptote is the ratio of the first terms, which is 1 over 1, which is just 1. So this horizontal asymptote is actually y equals 1. And now let's look for our intercepts. Let's look for the x-intercept and the y-intercept. So that x-intercept is the solution to the top. So I'm going to set that numerator equal to 0, and I'm going to solve for x. X equals -3. So I'm going to write that as an ordered pair. Remember, the x-intercept is when y is 0. So -3, 0 is that ordered pair. Let's go ahead and graph it. The y-intercept is when x is 0. So all I'm going to do here is plug in 0 for x, and I'm going to solve. 0 plus 3 over 0 minus 4 is 3 over -4, or -3/4. So if I write that as an ordered pair, I get 0, -3/4. And then if I graph that on my y-axis, if there's where -1 is, -3/4 is about right there. So now we're looking for any of those special squared terms where the entire factor is raised to a power that's a multiple of 2. Do I see any of that? I don't. So here's another example that does not contain multiplicity, which means what is my function going to look like? I've got the two asymptotes here. I know the function is going to pass through these 2 points at least. So once it passes through those 2 points, it's going to take that same general shape as your parent function. But where would the other part of the function be? I always have some students that want to graph it up here, like above the function. But if I were to graph it up there, would I even have a function? I would not have a function. It would not be a function. So I know the rest of this function is in this quadrant, if you will, over here, in that upper right. I don't know if I can erase all these dots here. Oh, it's not going to let me. So let's move on to our fourth example. And the fourth example is actually an example that contains multiplicity. But let's go ahead and work through our acronym here, AIM. So the A stands for asymptotes. So I'm going to look for the vertical and the horizontal asymptotes. So the vertical asymptote, I know my numerator, my denominator, remember x minus 3 squared is just x minus 3 times x minus 3. So all you're going to do is just set one of those equal to 0 and solve for x. So x minus 3 equals 0. When I solve for x, I get x equals 3. And then when I graph it, it's going to look like this. X equals 3. And now we're looking for if there's more on the bottom or if it's the same. And I'm talking about those exponents that are, or the degree of the numerator or the denominator. So there's obviously more on the bottom because there aren't even any variables on top. There's more on the bottom, which means my horizontal asymptote is y equals 0. Right here, y equals 0. And now let's look for those intercepts. We're going to look for our x-intercept. We're going to look for our y-intercept. The x-intercept is just the solution to the top. So we're going to set 5 equal to 0. But can 5 equal 0? It cannot. So we do not have an x-intercept. It does not cross our x-axis. Our y-intercept is when x is 0. So you have to be really careful here. I'm going to go off this function. So 5 over 0 minus 3 squared, which is 5 over -3 squared, which is 5 over what? Positive 9. So my y-intercept is 0, 5/9, which just it's just a little more than 1/2. So if there's where 0, 1 is, then 0, 5/9 would be like right there. So now I'm looking at the multiplicity here, and I can see that I do have a special squared term in my denominator. So I do have multiplicity in the denominator at x equals 3, at that asymptote. What does this mean? It means that the graph will meet at x equals 3. And here's what that looks like. So I'm going to do this right here. Okay, it's going to meet there. So I know I've got my vertical asymptote and the horizontal asymptote, and I've got this point right here that's graphed on my y-axis. So I know that I'm going to have the shape of my function to be something like this in that upper left. Whoa, goodness gracious. That is really bad. Let's see if I can erase that. In that quadrant up there. Let's try this again. Okay, let's see if I can do this a little better. Whoop, something like that. So previously, where would the other part of this function be? It would be in that lower right little quadrant, if you will, but because there's multiplicity in the denominator, the other part of my function will actually be over here. It's going to be the same side of that horizontal asymptote, obviously the other side of the vertical asymptote, but it's going to be the same side of that horizontal asymptote. So it's just right next to it, and it meets at that vertical asymptote. So let's move on to our last and final example, and that is a rational function with a hole. So the first thing you want to do when you're given a rational function is to factor everything. So obviously I need to factor that denominator. So x squared minus x minus 6, how is this going to factor? Well, if I rewrite my numerator, two numbers that multiply to -6 and add to -1 are 2 and -3. So x plus 2 times x minus 3. So in this case, I actually have the same factor on top as I do on bottom, and that's x plus 2. So if I cross those out and I rewrite this, my new function, if you will, is 1 over x minus 3. So I do have a hole. Where is the hole? X plus 2, what I'm going to do is I'm going to set that factor equal to 0. X plus 2 equals 0, and I get x equals -2. So there is a hole at -2, and now what I'm going to do is I'm going to find f of -2 in this new function. So 1 over -2 minus 3 is 1 over -5. So there is a new hole here. Let's write it down, with a hole at, and it's just the point on the graph where the function is undefined. Okay, there's not a point there. So there is a hole at -2, -1/5. So I'm just going to signify that when I'm drawing this function with just a little circle at that point. So now, given this new function up here, let's find the asymptotes, the intercepts, and if it has any multiplicity. So the asymptotes, vertical asymptote and a horizontal asymptote. And again, we're just going to look at this new function over here. So the vertical asymptote's the solution to the bottom. So x minus 3 equals 0. That asymptote is at x equals +3. So let's draw the asymptote there. X equals 3, and the horizontal asymptote, you can see that there's more on the bottom. So there's more on the bottom, which means what is that horizontal asymptote? Is it the ratio of the first terms, or is it y equals 0? It's y equals 0. So I know the horizontal asymptote is just that x-axis. So now let's look for our intercepts, the x-intercept and the y-intercept. So x-intercept is just a solution to the top. So we're going to set 1 equal to 0, and since 1 cannot equal 0, then I do not have an x-intercept. What's the y-intercept? I'm going to plug in 0 for x. So 1 over 0 minus 3 is just 1 over negative 3. So the y-intercept is 0, negative 1/3, and we can graph that. If there's 0, negative 1, then 0, negative 1/3 is like right there, something like that. So I've got my two asymptotes here, and you can determine, is there any multiplicity? There is not. There aren't any of those special squared terms. So I know that part of the function is going to be in this lower left quadrant, and it's going to look something like this. But what you have to be careful about is that at negative 2, you're actually going to have a hole right there. And that's how you would draw that. So there's the hole at negative 2, negative 1/5. Okay, you just signify it as an open dot. So since there's no multiplicity here, it's not going to meet at the asymptote, which means the other part of the function is across from it. Okay, remember, it's not going to be directly above it because that would not be a function. It's going to be across from it. So these rational functions with holes, what you have to remember is holes exist when the same factor exists in the numerator and denominator. Holes exist when the same factor exists. Okay, I was thinking I probably should reword that. In the numerator and the denominator. So what are you going to do? You cross them out. You solve for the x value in this factor. That's the x value of the hole. Then you're going to plug in the x value into your new equation and solve for the y value. That is the y value of the hole in the function. So that concludes your notes over day 1, graphing rational functions. I know it's a lot, but I hope it was helpful.